Hello everyone. This is NagaLakshmi Devi, Assistant Professor, Department of Freshman Engineering, IARE, Hyderabad, Telangana. Now already earlier we have discussed about the Taylor series and that expansions. This Taylor series expansion depending upon the up to infinity terms. Now the number of problems are there in Taylor series expansion. Now here same procedure we are following the Maclaurin series also. These are the Maclaurin series problems. What is the difference between Taylor series and Maclaurin series means here x minus a, z minus a in terms of Taylor series expansion. In that z minus 0 is the Maclaurin series. In that means a equal to 0. Otherwise z naught. We are considering a equal to z naught or something. If we both are in 0, then it is called Maclaurin series. Now here f of x equal to sin 2x means f of 0 equal to sin 0. Like that. Now the Maclaurin series also completed. Now the next method is Lorentz series expansion. Now the Lorentz series expansion proof statement also completed earlier section, but just we are discussing this statement and we can move the problems. If f of z is analytic on two concentric circles C1 and C2 with a center at z0 and also in the annular region R bounded by the C1 and C2, then at any point z in R, f of z can be expressed as a convergent series of positive and negative powers of z minus z0 in the form. Now this is the form f of z equal to, here two terms are there, an, bn. This is the complete expansion of the Lorentz series. Now the proof also completed, realization proof also completed. Now here proof also completed. Then by using this proof, we are solving the problem. These are by using Taylor series expansion, Lorentz series expansion is completed. These are the Lorentz series expansion problem. Now this is the problem. Find the Lorentz series for f of z equal to z square minus 1 by z square plus 5z plus 6 in the region 2 less than mod z less than 3. In the region here, the region is condition here 2, the z is in between of 2 and 3. Here the roots of this one, in denominator the roots of this one, z square plus 5z plus 6, the roots are z square plus 3z plus 2z plus 6. Here 3 into 2, 6 z square and addition is 5z. Now the roots are 3 and 5. Now common with z, that means z plus 3 plus 2, z plus 3. Z plus 2 into z plus 3 are the roots. Here the z equal to minus 2 comma minus 3. The roots are 2 and 3. Here it is involved with this one. Now numerator is different. F of z is completely depending upon the numerator and denominator individually. Here by using partial fractions means here numerator and denominator both have the order is same. Now we are not separating the partial fractions by using, but here by using division method, that is improper fraction because numerator is not numerator is equal to the denominator. That's why, but always the numerator always less than to denominator. But here not converted into like that. That's why by using division method, the division method is z square plus 5z plus 6 into z square minus 1. Now multiplication with 1. That means z square plus 5z plus 6. Now these two are cancelled. The remaining part is minus 5z minus 6 minus 1. It is minus 7. Now that is 1 minus of 5z plus 7 by z square plus 5z plus 6. Here like that one we get like that. Now here partial fractions are available. Why? Because numerator is lesser than to denominator order. That means by using this one 5z minus 7 equal to a of, now denominator is 1 minus of 5z plus 7 into denominator already we are calculating the roots, that is z plus 2 into z plus 3. That means here it is z plus 2, z plus 3 plus b into z plus 2. Now put here simplification is the simplest method is put z equal to minus 3. That means this total term is converted into 0. That means minus 5 into minus 3 minus 7. This term is 0 plus b into minus 3 plus 2. Minus 3 plus 2 means that is minus 1. Now it is total minus 15 minus 7. Minus into minus plus 15 minus 7, that is 8. 8 equal to b of minus 1, that equal to b equal to minus 8. b equal to minus 8. Now next one, b equal to minus 1, the first partial fraction is completed. Next, what about a? Now put z equal to minus 2. Minus 5 of minus 2 minus 7 equal to a of minus 2 plus 3. This term is 0, becomes 0. Then minus into minus plus 10. 10 minus 7, that is 3. 3 a of, this is 1. a equal to 3. a equal to 3, b equal to minus 8. Okay, that is the complete expansion. Now here we common with plus, that is minus of minus 7. Now applying that one. Then it is completed. This is the partial fraction of this completed f of z. By division method and applying partial fraction method also, this is the section. This can be solved by like this, by using division method and partial fraction method also. This is the expansion. Now how we can solve the expansion means, here the method is always we are depending upon the 1 minus x whole inverse, otherwise 1 plus x whole inverse method. Here denominator we are converting to two methods, two ways. Why? Because here 2 is less than mod z is converted, and mod z less than 3. That means 2 by mod z and z by 3. These two steps we are not forget that one. Why? Because the reason is lies between 2 and 3. That's why 2 less than mod z less than 3 means 2 divided by mod z, that is equal to 1, and another section is mod z is less than 3, that equal to 1. These two are either less than or greater than or anyone. We are solving like this. This is the conditions. Why? Because it is in between of z. 2 is lesser than z is 2 is lesser than to z, and 3 is greater than to z. That is the condition. That's why I am applying these two conditions. Now simplification also showing like that, 2 by z. That's why common with z. Now the common with z means 1 plus 2 by z, and here common with 3, the constant, denominator 3 is there, that's why constant 3, that means 1 plus z by 3. Now in denominator terms we are splitting in, converting into numerator term means 3 by z of 1 plus 2 by z whole inverse minus 8 by 3 1 plus z by 3 whole inverse. That is the condition. I am writing that one here. Now here onwards we know the procedure, that is 1 minus x whole inverse, 1 plus x whole inverse. Now the expansion is, what is the formula? 1 plus x whole inverse equal to 1 minus x plus x square plus x cube, minus, here it is minus x cube plus x power 4 minus x power 5, like that. Now applying that condition, that means that equal to 1 plus 3 by z into 1 minus 2x means here it is 2 by z. 2 by z plus 2 by z whole square minus 2 by z whole cube plus up to so on. Minus 8 by 3, same procedure, 1 minus z by 3 plus z by 3 whole square minus z by 3 whole cube plus up to so on. That is the condition. Now here that expansions can be written. Now here I am writing here 2 by z less than 1 and z by 3 less than 1. Earlier also I am writing that one. Oh, I cleared that one, but that one. So that the series converges absolutely. Yes, the series is convergent. 2 less than mod z less than 3. 2 by z is less than 1 and another one is z by mod z by 3 is less than 1. Both are convergent. Here we get that one also. 1 plus 3 by z into 1 minus 2 by z plus 2 by z whole square minus 2 by z whole cube plus up to so on. And another one is minus 8 by z, I think. Minus 8 by minus 8 by 3 1 minus z by 3 plus z by 3 whole square minus z by 3 whole cube plus up to so on. This is the expansion. Now 1 plus asterisk 3 by z asterisk. Now the expansion can be in terms of we are converted into summation method, that is summation n equal to 0 to infinity minus 1 whole power n, this one. Next 2 by z whole power n. Now I am substituting here n equal to 0 for example. Minus 1 to the power of 0, something to the power of 0 is nothing but 1. 1. Here also same 1. That is 1. The first expansion completed. Now n equal to 1. Minus 1, 2 by z. Minus 2 by z completed. N equal to 2. Minus 1 whole square, that is 1. 2 by z whole square, that is 1. This one. 2 by z whole square. Continuing this process. Now this is also satisfied. This one is satisfied. And next one, minus 8 by 3. Summation n equal to 0 to infinity. Same steps. Minus 1 whole power n, z by 3 whole power n. Now substituting here n equal to 0. N equal to 0 means minus 1 to the power of 0. Z by 3 whole power 0. Something to the power of 0 is nothing but 1. Next n equal to 2. N equal to 1. Sorry. N equal to 0 completed. Next n equal to 1. N equal to 1 means minus 1 whole power 1. That is 1 into z by 3 whole power 1. Plus minus n equal to 2. Minus 1 whole square. That is plus 1. Z by 3 whole square. Next minus 1 whole cube. Minus 1 into z by 3 whole cube. Plus up to so on. Now these steps also completed. Now this is the complete the law and series expansion of the given function f of z. Here two problems are there. The first one is find the law and series for f of z equal to x by f of z equal to 1 by z minus 1 into z minus 2 in the region 1 less than mod z less than 2. Now the solution here, f of z equal to the given function f of z equal to 1 by z minus 1 into z minus 2. Here partial fractions. We are solving the partial fraction method, that is 1 equal to a into z minus 2 plus b into z minus 1. Now here put z equal to 2. Put z equal to 2 means 1 equal to a value 0. Now b equal to 2 minus 1, that equal to 1. That implies b equal to, that implies 1 minute. That equal to b equal to 1. Next what about a? Here put again z equal to 1. That means b term completely 0. 1 equal to a into 1 minus 2. That is minus 1. That implies a equal to minus 1. Therefore, the function f of z equal to 1 by z minus 1 into z minus 2. The partial fractions values are minus 1 by z minus 1 plus b equal to 1. 1 by z minus 2. Here the two roots are this one. The two functions are this one. Z minus 1 and z minus 2. Here now substituting, now the method is, here the given condition is 1 less than mod z less than 2. That means 1 by z mod z less than 1. And another method is, another step is 1 by z 2 less than 1. These two conditions we are applying here. That means minus 1 by common with z by using this step. Mod z equal to 1 minus 1 by z. And another one is 1 by common with 2. That means 1 minus 2. Common with minus 2. That means 1 minus z by 2. Now here minus 1 by z into 1 minus 1 by z whole inverse minus 1 by 2 into 1 minus z by 2 whole inverse. Now the expansion is minus 1 by z into 1 minus 1. Here what is the formula of 1 minus x whole inverse? That is 1 plus x square plus x cube plus x power 4 plus up to so on. Now applying that one, 1 plus, what is the condition? 1 by z plus 1 by z whole square plus 1 by z whole cube plus up to so on. Now first step completed. What about next one? Minus 1 by 2. Similarly same condition, 1 plus z by 2 plus z by 2 whole square plus z by 3 whole cube plus up to so on. That is the complete expansion. Now this complete expansion can be converted into summation method, that is minus 1 by z of summation n equal to 0 to infinity minus 1 whole power n. We don't want that one. Why? Because all those terms are in positive steps. That's why we are removing that one. Direct step is Direct step is 1 by z whole power n. For example, we are substituting 0. Here 0 means something to the power of 0 is nothing but 1. 1 plus n equal to 1, 1 by z, n equal to 2, 1 by z whole square, 1 by z whole cube. Okay, now that condition is satisfied. Now 1 by 2 summation n equal to 0 to infinity. This is also z by 2 whole power n. Z by 2 whole power n means here n equal to 0. Z by 2 power 0, something to the power of 0, that value is 1. Next, z by 2 whole power 1, z by 2 whole power square, z by 2 whole cube plus up to so on. Now this is the complete expansion, series of expansion of Lorentz series. Problem of this one. F of z equal to 1 by z minus 1 into z minus 2 in the Asian 1 less than mod z less than 2. This is the complete problem. Now similarly, we can solve the second method, that is expand the Lorentz series for f of z equal to z square into e power 1 by z about z equal to 0. This condition is defined. Here about z equal to 0 condition is given. Now we can see this one also. Now the solution, given that f of z equal to z square into e power 1 by z, then clearly f of z is analytic at z not equal to 0. If it is z equal to 0, it is not analytic. Z equal to z not equal to 0, the function is analytic. Otherwise, it is not analytic. Why? Because denominator may be or numerator may be 0. It is not analytic. That's why compulsory the z condition is not equal to 0. But it is satisfied or not, we can see this one. Now, the function f of z equal to, here f of z equal to z square into e power j. E power x expansion is 1 plus 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus up to so on. 1 as it is 1 plus, here x is replaced by 1 by z here. That means 1 by z plus 1 by 2 factorial into here x square nothing but 1 by z, that is 1 square by z square, that is 1 by z square, plus 1 by 3 factorial into z cube plus up to so on. Continuing this process up to nth term, up to infinity. Now multiplied with the z square, in total this complete terms z square into 1, that is z square plus z plus 1 by 2 into z square get cancelled, plus 1 by 3 factorial into z square by z cube, that is we get only z, plus 1 by 4 factorial into z square minus up to so on, plus up to so on. Continuing this process, this is the required Lorentz series expansion at f of z equal to z equal to 0 condition. Maybe if it is z equal to 0, this one 0, 0, this one is infinity. Only we get 1 by 2 only. Now this is infinity. Something to the something plus infinity is nothing but total, it is infinity. That's why compulsory at z equal to 0, we are considering the Lorentz series expansion. Now that two problems completed, this is third one, important one. Expand z square minus 6z minus 1 by z minus 1 into z minus 3 into z plus 2 as power says in z in the region 3 less than mod z plus 2 less than 5. Here this is the conditions given. Solution z square minus 3z minus 6z minus 1 by z minus 1, z minus 3, z plus 2. Now the partial fractions. Here we are solving partial fractions method. Why? Because numerator is lesser than to denominator term. Here denominator z into z, that means z cube. Okay, numerator is lesser than to denominator. Then the partial fractions condition is satisfied here. That's why a by z minus 1 plus b by z minus 3 plus c by z minus 2. We get that one. The roots are, for example, we can see here z minus 1 into a into z minus 3 into z plus 2 plus b into z minus 1 into z plus 2 plus c into z minus 1 into z minus 3. Put z equal to 3. Now z equal to 3 means this one is u. Z square means here 3 square, that is 9. 9 minus 3 into 6, 18 minus 1 equal to this term 0. A into 0 plus b into 3 means 3 minus 1, 2 3 plus 2, 5. This is also 0. Only this one, 10b equal to 9 minus 8, 19, 9 over 10, minus 10. 10 by 10, b equal to minus 1. We can solve like this. Next, put z equal to, we can choose minus 2. That is minus 2 whole square. 4 minus into minus plus 12 minus 1 is equal to a into 0 plus b into 0 plus c into, here we can substitute z equal to 2 means minus 2 means minus 2 minus 1 minus 3 minus 3. Here it is minus 2 minus 1 minus 3. Now here it is minus 2 minus 3 minus 5. Overall it is minus 5. Now here it is minus plus 16 minus 1 15 equal to this one 0, this one 0, and minus into 3 into 3 into minus 3 into minus 5 15. C equal to 15, C into 15, then C equal to 1. B equal to minus 1 and C equal to 1 we get. And similarly again put this part complete. Put Z equal to 1. Z equal to 1 means here 1 square 1 minus 6 minus 1. Both are cancelled. Next A into Z 1 is there. 1 minus 3 minus 2. 1 minus 1 plus 2 3. Here 0, this one is 0, the B and 0, B and C both are zeros. Only minus 6 equal to minus 6A. Okay, both are cancelled. We get A equal to 1. A equal to 1, B equal to minus 1 and C equal to 1. Now substituting here 1 by Z minus 1 minus 1 by Z minus 3 plus 1 by Z plus 2. 1 minus 1, 1 the roots. That's one. 1 minus 1, 1 are the roots of partial fractions of the given function f of z. Now this is the important one. Here the given condition, see here, the condition is 3 less than mod of z plus 2 less than 5. Here given condition is 3 less than mod z plus 2 less than 5. Now I am using that one. 3 less than mod z plus 2 less than 5. That means now the notation is 3 by z plus 2 is less than 1 and another one is z plus 2 by 5 is less than 1. My condition like this, I am converting to like that means z minus 1. Minus 1 is there. I am adding plus 2 minus 3, we get minus 1. So converting to like this. Now 3 minus 3 we get means plus 2 minus 5. Z by 1 by z plus 2 is as it is, no changes. Now we can shift it into these two means, now count with the z plus 2, 1 minus 3 by z plus 2. Now we can count the 5. Minus 5 means minus 5 into, here minus already there, minus into minus plus 5. 1 by 5 into 1 minus of z plus 2 by 5 plus 1 by z plus 2 common as it is. Now here 1 by z plus 2 into 1 minus into inverse. Now we know that this expansion, that is 1 by z plus 2 into 1 minus of 3 by z plus 2 minus plus 3 by z plus 2 whole square plus minus up to so on. Next another one is minus plus 1 by 5 into 1 minus, over all are plus. Minus in minus minus is there. 1 minus x whole inverse expansion. Here also 1 minus x whole inverse expansion. 1 plus z by 2, z plus 2 by 5 plus z plus 2 by 5 whole square plus up to so on. Plus again 1 by z plus 2 is there. Now the complete expansion that can be written as 3 by z plus 2 whole power n minus not is this for plus 1 by 5 summation n equal to 0 to infinity z plus 2 by 5 whole power n plus 1 by z plus 2 is as it is. I am not changing this part. We can shift it means, so here we are also common with the 2, that is 1 plus z by 2, that equal to 1 by 2, 1 plus z by 2 whole inverse. Now the expansion is 1 by 2 into 1 minus z by 2 plus z by 2 whole square minus z by 2 whole cube plus up to so on, like that. Now the C is like that. Now it is valid for 3 by z plus 2 less than 1 condition and z plus 2 by 5 less than condition. Both conditions are satisfied. If both conditions are satisfied, then it is in between of 3 and 5 of z plus 2. Now this is the condition. This is also satisfied. Now another one is expand the Lorentz series for f of z equal to e power 2z by z minus 1 whole cube about z equal to 1. Also find the region of convergence. Here they are not, they are given in z equal to 1, only one region is there. Now we can convert it into f of z equal to e power 2z by z minus 1 whole cube. Now z minus 1 equal to, we are substituting t by using Lorentz is z equal to 1 plus t. Z equal to 1 plus t. Now f of z can be converted into in terms of e power 2z by z minus t, z minus whole cube equal to e power 2 into z is nothing but 1 t plus 1 or 1 plus t by z equal to 1 plus t. 1 plus t minus 1 whole cube. That means plus 1 minus 1 get cancelled. E power 2 into e power 2t. Splitting again two parts into t power cube. Now that equal to e square into e power 2t by t cube. Now that equal to e power e square into t cube into e power 2t. What is the expansion of e power x? 1 plus x by 1 factorial plus 1 factorial, this one. Next x square by 2 factorial plus x cube by 3 factorial plus up to so on. Now 1 plus 2t e power 2t. Here that is 2t by 1 factorial. X is here x can be replaced by 2t. That's why 1 plus 2t by 1 factorial plus 2t whole square by 2 factorial plus 2t whole cube by 3 factorial plus up to so on. That equal to, then we can simply write it as e square by t. T is nothing but here z minus 1. Then z minus 1 whole cube into 1 plus 2 into t is nothing but z minus 1. Z minus 1 by 1 factorial plus 2 into z minus 1 whole square by 2 factorial plus 2 into z minus 1 whole cube by 3 factorial plus up to so on. That is the final expansion of the given Lorentz series expansion. Okay, this is complete expansion. Now this can be written as, simply writing is like this. E square into summation n equal to 0 to infinity 2 by n factorial into t power of n by n into t power n minus 3. Now here t power n minus 3 means already t power n is there, t cube is there. Substituting in that one, we get t power n minus 3. Here t power n by t cube. T power n into t power minus 3. That equal t power n minus 3. That is the expansion here. Now replacing t equal to z minus 1, again substituting that one. Here z minus 1 is not equal to 0. Why? Because in denominator 1 by z is there. Here e square by t cube. T means z minus 1 whole cube. Now that maybe if it is 0, denominator 0 means the complete structure is infinity. That's why it is not equal to 0. The always z minus 1 is greater than 0 is the condition. Now this is the Lorentz series expansion of the another problem. Now the next one, two more problems are there. 7z minus 2. Here 7z, we can solve which one? This one. Already this method is completed. This method we can see this one. F of z equal to z square minus 1 by z plus 2 into z plus 3. That equal to, now the partial fractions method, that is z square minus 1 equal to a into z plus 3 plus b into z plus 2. Now put z equal to minus 3. In this condition, minus 3 whole square, that is 9 minus 1 equal to, this term complete a is 0. That means b into minus 3 plus 2 minus 1. This is 8. 8 equal to minus b. That implies b equal to minus 8. B completed. Now put z equal to minus 2. Minus 2 whole square means 4. 4 minus 1 equal to a into minus 2. Minus 2 plus 3. 1. This part is 0. That means a equal to 3. Therefore, f of z equal to a equal to 3 by z plus 2. B equal to minus 8. 8 by Z plus 3. Z plus 3. Now the given condition is mod Z greater than 3. That means here already 3 less than mod Z. That is the condition. That means 3 by mod Z. Now the splitting of that one is 3 by mod Z. Z common, we are common with that one. That is 1 plus 2 by Z minus 8 by. Here also we are common with nothing is there. That's why that is your choice. We can come with 3 better. 1 plus Z by 3. Already first problem method 3 by Z into 1 plus 2 by Z. 1 plus 2 by Z whole inverse minus 8 by 3. 1 plus Z by 3 whole inverse. Now onwards here it is completely first problem like that. Here first problem before 1 plus 1 is there. Now you will not get that one. Remaining as it is 1 plus x whole inverse expansion. 1 minus x plus x square minus x cube like that. Now here also same. Now then after expansion. That is 3 by Z. That is 3 by Z. 1 minus 2 by Z plus Z by 2 whole square minus up to so on. Next minus 8 by 3. 1 minus Z by 3 plus Z by 3 whole square minus up to so on. Minus up to so on. Now 3 by expansion. Now 3 by Z into summation n equal to 0 to infinity. Alternative plus or minus is there. That's why minus 1 whole power n into 2 by Z whole power n. Next similarly 8 by 3 summation n equal to 0 to infinity minus 1 whole power n into Z by 3 whole power n. Now this is the expansion. This is the problem of this one. Oh sorry, not this one, this one. F of Z equal to Z square minus 1 by Z plus 2 into Z plus 3. That is the complete problem of this one. Complete problem of this one. Like this. Similarly, we can solve this one also. Now, given f of z equal to 7z minus 2 by z into z plus 1 into z minus 2. Now, the condition is 1 less than mod z plus 1 less than 3. That is the condition. Now, 7z minus 2 equal to a into z plus 1 z minus 2 plus b into z minus 2 plus c into z plus 1. Now put z equal to minus 1. First step. What we get? Now substituting z equal to minus 1, a and c are zeros. We get b value. 7 into minus 1, that is minus 7 minus 2 minus 9. A value 0, c value 0, b value minus 1 minus 1 minus 2. Overall this is minus 3 plus the overall plus b equal to 3. b into 3. That implies b equal to minus 3. Minus 9 by 3, we get minus 3. Next, put z equal to 2. Now 7 into 2, 14 minus 2, 12. 12 equal to a part 0, b also 0, c equal to c into z equal to 2. 2 plus 1, 3. 2 into 3, 6. That implies c equal to 12 by 6. That equal to 2. C equal to 2. Next, put already z equal to minus 1 and z equal to 2 completed. Z equal to 0. Now put z equal to 0. That means here it is 0. Now 2 minus 2 only. Minus 2. This one is z equal to 0 means a into 0, 1 minus 2. That is minus 2. Total. That implies a equal to 1. 0, 0. Z equal to 0, 0. This one also 0. B and C are both are 0. Remaining b equal to minus 3, c equal to 2, a equal to 1. That means f of z equal to 1 by z minus 3 by z plus 1 plus not plus that one. Okay. Yes. Plus 2 by z minus 2. Now here given expansion is 1 by z plus 1 is less than 1. That is the first condition. And another condition is z plus 1 by 3 less than 1. That is the second condition. Now substituting that one here, this and this one. Here mod 1 by z is common, that one. We are not solving that one. Why? Because z equal to 0 condition is applied here, that one. Now here z plus 1. Now z plus 1 means 3 by, not that one. We are applying here better. Not common that one. Here this one. Z plus 1 minus 1. We are adding and subtracting this one. and minus 3 by here again z plus 1 is denominator is there by 3 means z plus 1 plus minus 3. Okay. In denominator we get 3 means minus 2 means minus 2 means plus 3 minus 2 we get that also we are splitting that one plus 2 by now it is no use for this one 2 by z minus 2 now common with z plus 1 here a direct step is there both are direct steps why I am using waste of my time here z is 1 by z into now 1 by z into minus 3 into z plus 1 whole inverse and 2 into now denominator common with minus 2 that means 1 minus 2 z by 2 now that is 1 by z inverse into minus 3 into 1 plus z whole inverse minus 2 by 2 to get cancelled next 1 minus z by 2 whole inverse this is the expansion now z inverse that is only z inverse minus 3 into 3 into z inverse both are same z inverse is same now here 3 into 1 plus 1 minus z plus z square plus z cube minus z cube here minus z cube plus up to so on next another one minus 1 plus z by 2 plus z by 2 whole square plus up to so on. Now this is the complete expansion. Now here it is satisfied by 1 less than mod z plus 1 minus less than 3. Now the series is completed. Now this is the complete Lagrange series expansions. 1 by here also same 1 by z plus 1. Now here 3 not common with 3 that is but z by 2 we common that one we have completed that one. Now this is the complete series of the section. These are the Lagrange series expansions. Total 4 or 5 problems are there. Now the best problem is first problem is more important and the third one also more important. This one and this one more important one. These are the Lagrange series problems. Complete Lagrange series problems. These are the complete Lagrange series problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.